Hello guys, welcome back to my channel Algorithm Avenue. In this video, we'll be discussing about another important and interesting topic, that is batch normalization. Okay, now let's start with the basic definition of batch normalization. It is an algorithmic method which makes the training of deep neural networks faster and more stable. Okay, faster and more stable means because of using this batch normalization in our artificial neural networks, the training becomes faster and also stable. Okay, now let's say before applying the batch normalization, the training time is 2 seconds. Okay, after applying the batch normalization, it reduces to, let's say, 1.2 seconds. Okay, means basically the training time is reduced due to batch normalization. Okay, training time is reduced due to batch normalization and also more stable training. Okay, and also more stable training. Now let's say this is our contour plot and this point is our global minimum. Okay, now before applying the batch normalization to our artificial neural network, the gradient descent may take more noisy steps to reach this global minima point. Okay, now after applying the batch normalization to our artificial neural network, it takes less noisy steps to reach to this global minima point. Okay, now due to this low noise in the gradient descent, the training becomes faster and also more stable. Okay, training becomes faster and also more stable. Okay, it consists of normalizing activation vectors from hidden layers using mean and variance of current batch. This normalization step is applied right before after the non-linear activation function. Okay, now I'll be explaining this part with a simple example. Now let's say this is our hidden layer. Okay, this is our hidden layer of a deep artificial neural network. Now we apply this batch normalization right after the hidden layer. Okay, we apply this batch normalization right after the hidden layer. Okay, we need to consider this batch normalization as a separate layer in deep learning. Okay, this batch normalization is considered as a separate layer in deep learning. Okay, now this is our hidden layer and correspondingly we apply batch normalization layer. Okay, now this batch normalization is applied in two steps. Okay, in step 1 we apply it on weighted sums. Okay, we apply it on weighted sums. In the step 2, okay, in the second approach, okay, this is the first approach, and in the second approach we apply it on the activation function outputs. Okay, activation function outputs. In the first approach, we apply it on the weighted sums, and in the second approach, we apply it on the activation function outputs. Okay, now how it is basically applied is, now the weighted sum is calculated. Now after calculating the weighted sum, we normalize the vectors. Okay, we normalize the weighted sums. Okay, how do we normalize this weighted sums? With the help of mean and variance. Okay, with the help of mean and variance, we normalize the weighted sums. Okay, now normalization means mean is equal to 1, sorry, mean is equal to 0 and standard deviation is equal to 1. Okay, mean is equal to 0 and standard deviation is equal to 1. Means all the vectors, okay, all the weighted sums are mean centric. Okay, all the weighted sums are mean centric. Okay, mean is equal to 0 and standard deviation is equal to 1 for weighted sums. Okay, now let's say in the second approach we choose activation function outputs. Okay, now after calculating the weighted sums, we need to pass it to activation function. Okay, after passing it to activation function, we will be getting some vectors, means some numerical values. Now on that numerical values we apply batch normalization. Okay, this is the second approach. Okay, in the first approach we apply it on the weighted sums, and in the second approach we apply it on the activation function outputs. Okay, means we use mean and variance for the normalization. Okay, we use mean and variance for the normalization. Okay, after applying the mean and variance, okay, after using the mean and variance to normalize, the entire data becomes mean centered, sorry, zero centered. Okay, entire data becomes zero centered. Okay, this is basically the entire concept of batch normalization. Okay, now let's see the evolution of batch normalization. Means from where did this researchers and scientists got the idea of discovering this batch normalization concept? Okay, now let's take an artificial neural network. Now to train this artificial neural network, I need some certain data. Okay, now I'll be training this artificial neural network with this data set. Okay, now in this entire training process I'm not normalizing the inputs. Means normalizing the inputs refers to mean is equal to 0 and standard deviation is equal to 1. Normalization of some numerical value means mean is equal to 0 and standard deviation is equal to 1. Okay, now in this entire training process I'm using unnormalized data. Okay, now when I train an artificial neural network with this unnormalized data, the contour plot, okay, the contour plot of the unnormalized data set training of an artificial neural network would be this. Okay, this is the contour plot of training an unnormalized dataset to an artificial neural network. Okay, now this is my global minima or local minima. Okay, now the gradient descent initially, let's say it starts from here. Okay, this is the starting point of the gradient descent and this is the global or local minimum. Okay, now let's say I choose learning rate as higher. Okay, why did I choose learning rate as higher? Means from this point to this point the distance is larger. Okay, now to cover this larger distance the gradient descent must take some larger steps. Okay, so for that I choose learning rate to be little higher. Okay, now when I choose learning rate to little higher, the gradient descent takes these kind of steps. Okay, these kind of steps means you can clearly see that it is overshooting. Okay, it is overshooting. Okay, now why it is overshooting? Because it is an oval shaped contour plot. Okay, it is an oval shaped contour plot, so that is why when I choose larger learning rate it is overshooting. Okay, now let's say I have started my gradient descent from this point by choosing smaller learning rate to prevent this problem of overshooting. Okay, now when I start from this point with a smaller learning rate, as from this point to this point the distance is larger, the gradient descent takes smaller steps. Now due to the smaller steps and the distance being larger, the training time increases. Okay, training time increases. Okay, training time increases and also unstable training. Okay, unstable training. Now same in the case of this, when I choose larger learning rate, okay, the training time will be higher. Okay, due to more noise the training time will be higher and also training will be more unstable. Okay, the training will be more unstable. Why? Because of choosing the unnormalized inputs. Okay, because of choosing the unnormalized inputs to train an artificial neural network. This is the contour plot I got. Okay, the contour plot due to unnormalized data will be this oval shaped curve. Okay, this will be oval shaped curve. Okay, now let's say I have normalized the inputs. Okay, normalizing the input means mean is equal to 1 and standard deviation is equal, sorry, mean is equal to 0 and standard deviation is equal to 1. Now the contour plot produced due to normalization of the data is a uniform concentric circle. Okay, it's an uniform concentric circles. Okay, this is the contour plot. Okay, this is the contour plot by normalizing the inputs. Okay, now let's say this is our global minima or local minima point. Okay, now let's say we are starting the gradient descent from this point. Okay, now I'll be taking two cases. Okay, first with larger learning rate and also smaller learning rate. Okay, now first I choose larger learning rate. Okay, now when I choose larger learning rate, again the gradient descent will take larger steps. Okay, the gradient descent will take larger steps, but in any point, okay, at any point it is not overshooting. Okay, at any point you see it is not overshooting because the circles are uniform, because the contour plot is uniform. As the contour plot is uniform, the gradient descent is unable to overshoot. Okay, the gradient descent is unable to overshoot. Okay, now this is with learning rate is equal to larger. Now let's say I'll be taking smaller learning rate. Okay, I'll be choosing smaller learning rate. Now this is the point from where the gradient descent starts. Now when you compare the distance from this point to this point, you see it is pretty less. Okay, when compared to this distance is very much less. Means when I choose smaller learning rates, okay, even when I choose smaller learning rates, the training time would be less. Okay, even with smaller learning rate, I will be able to reach this global minimum point with gradient descent algorithm. Okay, when I choose smaller learning rate, I'll be reaching this global minimum point with my gradient descent algorithm. Okay, this is the advantage of normalizing the inputs. Okay, this is the basic advantage of normalizing the inputs, that is mean is equal to 0 and standard deviation is equal to 1. Okay, now what scientists or researchers observed here is, when I normalize the inputs, okay, when I normalize the inputs that are given to my artificial neural network to train, my training is happening more, okay, more stable when compared to this. Okay, when compared to this is more stable, and even the training time is being less. Okay, the training time is being less. Okay, now what idea the scientists or researchers got is, now when I apply this normalization to the another set of numerical values in an artificial neural network, I will be able to get more stabilized training and less training time. Okay, now what are the numerical values is activation function outputs. Okay, activation function outputs. Basically, instead of saying activation function outputs, we can say it as node outputs. Okay, node outputs, that means hidden unit outputs. Okay, now when I normalize this hidden unit outputs, I'll be getting more stable training as well as less training time. Okay, this is how the batch normalization concept evolved, and this is entire the evolution of batch normalization. The two basic advantages of applying batch normalization to an artificial neural network is it reduces the training time and also stabilizes the training. Okay, other than these two advantages, it has another advantage, that is it solves the problem of internal covariate shift. Okay, batch normalization solves the problem of internal covariate shift. Okay, now before understanding what actually is this internal covariate shift, first let's understand what is this covariate shift. Okay, what is this covariate shift? Okay, yeah, now let's say this is our data set. Okay, this is the distribution of our data set. Now in our data set, we basically have two classes. In the first class we have black dots, in the second class we have blue dots. Okay, and this entire is my distribution of the input data. Okay, this is my distribution of the test data, sorry training data. This is the distribution of the training data. Okay, now I have trained a model. Okay, I have trained a classification model on this data. Okay, on this data set. Now after the entire the training process, I have got this classification boundary. Okay, this is the classification boundary of the classification model. Okay, on this distribution. Okay, on this distribution, this is my classification boundary. Okay, now this is the entire training process. Okay, this is entire training process. Okay, now at the time of testing, okay, at the time of testing, yeah, what actually happened is I have got some completely different distribution of data. Okay, now here when you clearly see, this is my training data distribution and this is my test data distribution. Okay, my training data distribution and test data distribution are completely different. Okay, are completely different. Okay, now when the distributions are different, okay, and when the distributions are different and when the classification boundary is same, you might think that there is no problem in it. Okay, here my training data distribution is in this way. Okay, my training data distribution is in this way and this is my classification boundary, and my test data distribution is in this way and this is my classification boundary. Okay, here it is producing 100% accuracy, and on the test data it is producing 100% accuracy. Okay, you see there is nothing problem over here, but there is a problem. Okay, there is a problem over here. Okay, now when you see completely different distribution on the test data, okay, in the test data if you see completely different distribution, you need to retrain the entire model on this data set. Okay, when at the time of testing, if you see a completely different distribution data, you need to again retrain the entire model on this differently distributed inputs, okay, on sorry, on this differently distributed data. Okay, now this is what the covariate shift. Okay, this is what the covariate shift is. Okay, now let's see with an example. Okay, I'll be explaining this covariate shift with a simple example. Okay, now let's say we are building some classification model. Classification model. Now, what this classification model should do is it must classify roses and other flowers. Okay, roses and other flowers means in our data set we have two classes. Okay, we have two classes. One is roses and other is other flowers. Okay, the other classes other flowers. Okay, now we have trained this. We have trained a classification model on this data set. Okay, now after entire training process we have checked our data. Okay, we have checked our data. Okay, now when we checked our data we have seen that the roses all are red. Okay, in our training data all the roses are red. Okay, and other flowers are some jasmine or some kind of flowers. Okay, means in our training data I have seen entirely red roses. Okay, the entire training data contains only red color roses and other flowers. Okay, now what my classification model understands is when roses are red then they are called as roses. Okay, means it doesn't call white roses or yellow roses as roses. Okay, it doesn't consider these color roses as under roses class, but they are actually roses. Okay, this white and yellow roses are also roses, but as my classification model is trained only on red roses, it considers only red color roses as roses and it classifies this white roses and yellow roses as other flowers. Okay, means here the red roses are referred to as this input distribution. Okay, this training data distribution, and this other color roses are referred to as this test data distribution. Okay, now you can see that you can clearly understand the problem of covariate shift. Okay, you can clearly understand what covariate shift problem is. Okay, now let us see what actually is this internal covariate shift. Okay, we have seen what is covariate shift. Now let us see what actually is this internal covariate shift. Okay, now for this I'm considering some deeper artificial neural network. Okay, this is my deeper artificial neural network. Yeah, it contains a number of hidden layers and it contains n number of hidden units. And let's say, yeah, let's say the inputs are x1 and x2. Okay, x1 and x2 are my inputs to this entire artificial neural network. Okay, now what we will be doing is we'll be dividing this deeper neural network into two parts. Right, this is my B neural network and this is my A neural network. Okay, this entire part is my B neural network and this entire part is my A neural network. Okay, now if you keenly observe, for my B neural network the inputs are coming from these two nodes. Okay, the outputs of these two nodes are the inputs to this B neural network, and to the A neural network the inputs are coming directly from the data. Okay, now what actually the problem is, now in the first epoch training, okay, I'll be forward propagating, right? I'll be forward propagating. Let's say the output distribution of this first hidden layer. Okay, the output distribution of this first hidden layer, let's say it is in this way. Okay, and the distribution has changed when it comes to second hidden layer. Okay, when it comes to second hidden layer the entire distribution has been changed. Now what actually happens is this B neural network get trained on this distribution. Okay, this B neural network get trains, okay, means it trains on this distribution. Right, now we have completed our first epoch. Okay, we have completed one forward propagation. Now in an epoch we will be having two steps. One is forward propagation and other is backward propagation. Now at the forward propagation this distribution is my input. Right, now at the time of backward propagation all the parameters gets updated. Okay, all the parameters are updated at the time of back propagation. Okay, after back propagation, okay, after one back propagation, all the weights will be updated, right? Now in the second epoch, okay, in the second epoch, these inputs are multiplied with the updated weights and bias values, so my distribution changes. Now in this case, the distribution changes to this way, and again the distribution changes to this way. Now what actually happens is, this entire bean neural network get trained on this, okay, will be trained on this distribution. Means at the first epoch, I'm training this bean neural network on different distribution, and at the second epoch, I'm training my bean neural network on different distribution. Okay, again in the third neural network and the fourth neural network, I'll be training my bean neural network on different distributions. Okay, now this is where the problem comes. Okay, this is the internal covariate shift. Okay, this internal covariate shift refers to training the model, okay, training the artificial neural network on different distributions. So training the model, artificial neural network on different distributions causes unstable training, as it sees different distribution data at the each epoch training. This causes unstable training. Okay, this causes unstable training means at the final test, means at the time of prediction. Okay, the final part when we are predicting it, it won't be able to predict well. Okay, it won't be able to predict well, won't predict well. Okay, this entirely is the problem of internal covariate shift. Okay, now how batch normalization solves this problem of internal covariate shift is, now actually we apply batch normalization after the hidden layers, right? Now after the first hidden layer, let's say we apply batch normalization. After the second hidden layer, we apply the batch normalization. Now at the first epoch training, right, my input data goes to my first hidden layer, and I'll be multiplied with weights and bias, and I'll be getting this distribution. Okay, I'll be getting batch normalized distribution. Okay, the output of this two of my first hidden layer is normalized, so my distribution will be normal distribution. Okay, now this normally distributed data goes to the second hidden layer. Okay, now with the second hidden layer also, I'm applying batch normalization, so my distribution changes to normal distribution. Okay, means at the first epoch training, I'm sending normally distributed data to bean neural network. Okay, now at the second epoch, I'll be updating my weights and bias values. Right, now after updating the weights and bias values, my distribution changes. Okay, right, my distribution is changing. Okay, now when I pass this changed distribution to this batch normalized layer, again my neural network, okay, again this batch normalized layer, what it does is it normalizes the distribution. Okay, now again when I pass this normalized distribution to the second hidden layer, again the weights and bias gets multiplied, and again the distribution changes. Now again after passing this through the second batch normalized layer, again the distribution will be normalized. Means each epoch training to this bean neural network, we are sending constant distribution, that is normalized distribution. Okay, so due to this we see stable training. Okay, we'll be seeing stable training. Okay, this is how the batch normalization solves the problem of internal covariate shift. Okay, now let us discuss how actually this batch normalization technique works. Okay, now to understand this batch normalization, we need to discuss 2 points. Okay, to apply batch normalization, we need to use mini batch gradient descent technique. Okay, mini batch gradient descent training technique. Okay, to apply batch normalization, we need to use mini batch gradient descent technique. Okay, and the second point is, we can apply this batch normalization to n number of layers in an artificial neural network. Okay, now let's say we have 10 layered artificial neural network. Okay, now in this 10 layered artificial neural network, we can apply this batch normalization to all the 10 layers, or we can apply to 6 layers, or it may be 4 layers. So applying this batch normalization to any n number of layers, it will depend on us. Okay, batch normalization can be applied to n number of layers. Okay, n number of layers. Okay, the first point is to apply batch normalization we need to use mini batch gradient descent technique, and second point is batch normalization can be applied to n number of hidden layers in an artificial neural network. Okay, these are the 2 points. Okay, now let us discuss this working of mini batch, sorry, batch normalization. Okay, now let's say this is our data set. Okay, in our data set we contain two features and this is our output variable. Okay, number of rooms and number of floors are our two features and price is our output column. Okay, now let's say this is our artificial neural network and we train this data set. Okay, sorry, we train this artificial neural network on this data set. Okay, this is my x1 feature and this is my x2 feature. Okay, now in this two layered artificial neural network, let's say, okay, let's say we are applying batch normalization over here. Okay, now for my first hidden layer I am applying batch normalization. Okay, and z11 and z2, sorry, z12. Okay, z11 and z12 are the outputs of this hidden unit. Okay, z11 is the weighted sum output and z12 is the weighted sum output of this hidden unit, and this is our batch normalization layer. Okay, now let us see how actually the flow of batch normalization, okay, how actually this entire flow is. Okay, how from inputs we'll be getting the outputs of this batch normalization. Okay, initially let's start with our first approach. Okay, first approach. Yeah, in our first method we'll be passing the inputs. Now the inputs get multiplied to weights and we'll be getting z11. Okay, it may be z11 or z12. Okay, this z11 and z12 are the weighted sum outputs. Okay, now from this weighted sum outputs, okay, now from this weighted sum outputs I'll be getting normalized, okay, normalized z11 and z12. Okay, from this weighted sum I'll be getting normalized weighted sums. Okay, I'll be explaining how actually we'll be getting this normalized weighted sum outputs. Okay, so in our first method, okay, in our first method we'll be applying this batch normalization on the weighted sums. Okay, after that we'll be passing through an activation function. Okay, after that we'll be passing through an activation function. Okay, after passing through the activation function I'll be getting activation function output. Okay, first we'll be calculating the weighted sums and from the weighted sums we'll be deriving normalized weighted sums. Okay, normalized weighted sums. On the normalized weighted sums we'll be applying activation function and we'll be getting the activation function output. Okay, this is our first approach. Okay, this is our very first approach. Okay, now in our second approach, okay, now when it comes to our second approach, this is our second method. Yeah, now in our second method same, we'll be calculating z11 and z12. Okay, now after calculating z11 and z12 we'll be not applying the normalization. Okay, we'll be not normalizing the weighted sums. Okay, we'll be directly passing this weighted sums to through the activation function. Okay, we'll be passing the weighted sums through the activation functions. Okay, after passing it through the activation functions we'll be getting a11 output and a12 output, right? Now on this activation function outputs we'll be applying the batch normalization. Okay, after deriving the activation function outputs we'll be applying batch normalization. Okay, so from that we'll be getting a11 normalized and a12 normalized. Okay, this is our second approach. Okay, batch normalization can be applied in two methods. This is our first method and this is our second method. Okay, but most frequently, okay, most used approach is this first approach. Okay, most widely this approach is used. Okay, this approach is not much preferred. Okay, now how are we actually deriving from z11 and z12 this z11 and z12 normalized? Okay, how are we actually getting this z11 normalized and z12 normalized? Okay, z11 normalized. Okay, I'll be explaining with respect to z11. Okay, same follows for the z12 as well. Okay, z11 is equal to z11 minus mu divided by standard deviation. Okay, the z11 normalized is obtained by subtracting the actual weighted sum. Okay, actual weighted sum, that is the direct weighted sum that we'll be getting from this hidden unit, subtracted by mean. Okay, this mu is nothing but mean and divided by standard deviation. Okay, divided by standard deviation. Okay, z11 normalized is equal to z11 minus mu divided by standard deviation. Okay, now you may have a doubt that how are we actually getting this mean and standard deviation values? Okay, now in determining this mean and standard deviation values involves this mini batch gradient descent. Okay, now how this mini batch gradient descent is helping to contribute in this mean and standard deviation is, first we initially select batch size. Okay, we initially select batch size. Okay, let's say batch size is equal to 4, right? We initially select batch size and let's say batch size is equal to 4. Now in this data set I'll be selecting 4 columns. Okay, this is my, sorry, 4 rows. This is my first row, second row, third row and 4 rows. Okay, I'll be selecting this first 4 rows for my initial train. So my initial input matrix becomes 4 cross 2 input matrix. Okay, where 4 rows and 2 columns. Okay, 4 rows and 2 columns. The 2 is nothing but total number of features. Okay, this is my input matrix. Okay, this is my input matrix. Okay, now input matrix passes through this artificial neural network, right? Now I'll be multiplied with this weights. Okay, now to this input matrix I'll be multiplied with weights. Okay, how many weights I have over here? 1 2 3 4. So it will be an 2 cross 2 matrix. Okay, I'll be multiplied with an 2 cross 2 matrix. Okay, so the resultant matrix is a 4 cross 2 matrix. Okay, the resultant matrix is a 4 cross 2 matrix. Now to this 4 cross 2 matrix I'll be adding the 1 cross 2 bias. Okay, first generally we multiply input with weight and add the bias. So I'm multiplying input with the weight matrix. After multiplying with the weight matrix I'll be adding the bias to it. So the bias matrix is an 1 cross 2 matrix and the resultant matrix is an 4 cross 2 matrix. Okay, the resultant matrix from this hidden layer, okay, the output of this hidden layer is an 4 cross 2 matrix. Okay, now let us see how are we actually calculating this mean and standard deviation. Okay, now let's say the 4 cross 2 matrix looks in this way. Okay, z1 z1 z2 z3 z4 z5 z6 z7 z8. Okay, let's say these 8 values. Okay, 4 cross 2 matrix, this is my 4 cross 2 matrix which ranges from z1 to z8. Okay, these are all the numerical values in this 4 cross 2 matrix. All right, now let us take this first column. Okay, let us take this first column. Okay, this first column is the output of this hidden unit. Okay, this first column is the output of this hidden unit. Okay, now what actually happens is, yeah, z1 z2 z3 z4 must be subtracted with, okay, must be subtracted with mean. Okay, now from where I'll be getting this mean is, I'll be calculating the mean from this all 4 numerical values, that is z1 plus z2 plus z3 plus z4 divided by 4, total number of quantity. Okay, from this I'll be deriving mean. Okay, from this let's say mean is equal to z. Okay, for this 4 numerical values I'll be calculating the mean, okay, and I'll be subtracting it from Z1, Z2, Z3 and Z4 subsequently. Okay, after that I'll be calculating, okay, after that I'll be calculating standard deviation from this four numerical values and I'll be dividing it with standard deviation. Okay, first I'll be considering this first row of the matrix, sorry, first column of the matrix, and for the first column I'll be subtracting the mean and divided the standard deviation. Okay, this is with respect to this hidden unit. Now for this hidden unit I'll be selecting this matrix and I'll be replacing this matrix with this matrix and I'll be calculating the mean and I'll be subtracting the mean and I'll be dividing with the standard deviation. Okay, this is how the entire flow goes. Now let's say if I have third unit, okay, if I have third hidden unit over here, I'll be getting another matrix over here. Okay, that may be Z9, Z10, Z11, Z12. Okay, I'll be getting another column of matrix, that is Z9, Z10, Z11, Z12. Okay, now in this way the mean and standard deviation are calculated. Okay, now in this entire process, okay, in this entire process there is another twist over here. Okay, now from Z11 we'll be calculating Z11 normalized. Okay, after calculating this Z11 normalized, again we have another step in between. Okay, in between Z11 normalized and applying activation function to this Z11 normalized, I'll be having another step present over here, that is Z11 batch normalized. Okay, Z11 batch normalized. This Z11 batch normalized is calculated by gamma into Z11 plus beta. Okay, gamma into Z11, sorry, Z11 normalized plus beta. Okay, so the entire flow becomes, first Z11, from Z11 we'll be deriving Z11 normalized, from Z11 normalized we'll be deriving Z11 batch normalized, and from Z11 batch normalized we'll be applying activation function to this Z11 batch normalized. Okay, g of Z11 batch normalized, and we'll be deriving A11 output. Okay, this is entire flow. Okay, now let us see what actually this equation specifies. Okay, now we will be having some special terms over here. Okay, gamma and beta. Okay, this gamma and beta are nothing but the reverse operations of this mean and standard deviation. Okay, these are the reverse operations of this normalization. For normalization and batch normalization, okay, this normalization and batch normalization are reverse operations. Okay, in normalization we subtract with the mean, here we are adding with the bias, sorry, beta, here we are adding with the beta, here we are dividing with the standard deviation, here we are multiplying with the gamma parameter. Okay, here we are dividing, here we are multiplying, here we are subtracting, here we are adding. Okay, so this normalization and batch normalization are reverse operations. Okay, now what is the advantage of using this reverse operations is, sometimes the neural networks doesn't expect the inputs to be normalized. Okay, always this neural networks doesn't want to train on the normalized inputs, so sometimes they expect some unnormalized inputs. Okay, so for unnormalization, okay, here we are normalizing to prevent this normalization. Okay, to unnormalize the inputs we use this gamma and beta parameters. Okay, now how they actually unnormalize this normalized data is, here this gamma value, okay, this gamma value initial value is 1 and this beta initial value is 0. Okay, this gamma initial value is 1, this beta initial value is 0. So in the further steps of the training, okay, in the further steps of the training, the neural network understand what data it must expect. Okay, whether it may be, like it may be trained on normalized data, or it can be trained on unnormalized data. Means after some steps of training, your neural network itself understand whether it must be trained on the normalized data or it must be trained on the unnormalized data. So if it must be trained on the normalized data, the gamma and beta parameters till the end of the training, okay, when gamma is equal to 1, I'll be getting Z11 batch normalized is equal to Z11 normalized, right? Z11 batch normalized is equal to Z11 normalized. Okay, means when your neural network entirely expect normalized data, so at the end of the training, okay, the end of the training itself, the gamma and beta parameters will be same as the initially initialized values. Okay, now when we initialize 1 and 0 to this gamma and beta parameters, they'll be equal to z11 batch normalized is equal to z11 normalized. Now let's say your neural network is expecting some unnormalized data. When your neural network expects some unnormalized data, there will be some value assigned to this gamma and beta parameters. Okay, sorry, this gamma and beta parameters are trainable parameters. Okay, trainable parameters. The neural network itself will understand whether it expects the normalized inputs or unnormalized inputs. When it expects normalized inputs, the gamma and beta parameters will be 1 and 0 till the end of the training. And whether it expects, okay, whether it expects some unnormalized inputs, the gamma and beta values are trainable parameters and will attain some values. Okay, will attain some numerical values. So then it becomes z11 batch normalized is not equal to z11 normalized. Okay, so when so based on the expectation of the neural network, we'll be adjusting this gamma and beta parameters. Okay, this gamma and beta parameters are trainable parameters. Okay, so this is entire batch normalization. Okay, same as how it worked for the two-layered artificial neural network, same works for the deeper neural network as well. Okay, same entire procedure will be same for and deeper artificial neural network as well. Okay, so this is entire batch normalization. Okay, till now we have discussed how batch normalization works for the training. Now let us discuss how batch normalization works at the time of testing. Okay, now let us say we have the same dataset which contains two columns and one output label. Okay, one output label, and we have chosen 100 rows of data. Okay, we have chosen 100 rows of data for training with batch size is equal to 4. Okay, with batch size is equal to 4. Now now let's say in my first epoch I'll be training 25 times. Okay, I'll be training 25 times. Why I'll be training 25 times? Because I have the batch size as 4. First I'll be taking first 4 rows of data, second I'll be taking second 4 rows of data. So in this way I'll be taking till my 100 rows of data is completed. Okay, I'll be taking till my 100 rows of data is completed. So 100 divided by 4 is 25, means I'll be training in an epoch 25 times. Okay, I'll be training this entire data set in an epoch 25 times. Okay, now I'll be getting after, okay, in yeah, now I'll be getting 25. Okay, 25 mu and 25 sigma values, right? Why I'll be getting 25 mu and sigma values? First I'll be sending my first batch. Okay, first I'll be sending my first batch into my artificial neural network. So I'll be getting my first mean and first standard deviation value. Second, I'll be choosing another 4 rows of data. Okay, after that I'll be getting mu2 and sigma 1. Third, I'll be choosing another 4 rows of data and I'll be getting mu3 and sigma 3. So in the similar way, as I'm having 25 batches, okay, as I'm having 25 batches, I'll be having 25 mu, okay, 25 mean values and 25 standard deviation values. Okay, in an epoch I'll be having 25 mean values and 25 standard deviation values. Okay, now at the end of the epoch, okay, at the end of the epoch I'll be getting these 25 values, right? Now at the end of the epoch, what actually happens is we calculate exponential, okay, exponential weighted moving average. Okay, now for this 25 mean values and 25 sigma values, we'll be calculating exponential weighted moving average. Okay, I'll be explaining this exponential weighted moving average in the further videos. Okay, now just remember that for this 25 mean values and 25 sigma values, I'll be calculating exponential weighted moving average. So at the end of first epoch training, I'll be getting a fixed mu value and fixed standard deviation value. Okay, and at the end of first epoch training, from this 25 mean values, I'll be deriving one fixed mean value, and among this 25 standard deviation values, I'll be deriving one standard deviation value. Okay, now let's say I'm training for 100 epochs. Okay, now at the end of 100 epoch training, what the mean and standard deviation value I'll be calculating, okay, I'll be deriving, that is fixed for testing. Okay, that value is fixed for testing. Okay, that value is fixed for testing. Okay, at the end of 100th epoch, what the value I'll be getting for mu and sigma, that value is considered for testing. Okay, yeah. Now let's take an example. Okay, let us take an example. Now let's say we have artificial neural network. Okay, let's say this is a hidden layer of an artificial neural network. Okay, now this first hidden unit, now for this first hidden unit I'll be having some mu and sigma values, and I need to also carry gamma and beta values. Okay, now again for this second hidden unit, okay, now again for this second hidden unit I'll be getting, okay, I'll be getting another set of mu and sigma values. Okay, I'll be getting another set of mu and sigma values. Okay, the mu and sigma values for this hidden unit and this hidden unit are not the same. Okay, for this hidden unit and this hidden unit, and now let's say if I have another hidden unit, now for all these three hidden units the mu and sigma values, okay, the mean and standard deviation values are not the same. Okay, also we'll be having gamma and beta values. Okay, these two are parameters and these two are trainable parameters. Okay, these two are parameters and these two are trainable parameters. Means at the time of testing each hidden unit must carry all these four values. Okay, at the time of testing each hidden unit must carry all these four values, where I'll be getting fixed, okay, I'll be getting fixed mu and sigma values for an hidden unit. Okay, fixed mu and sigma values for an hidden unit. Okay, fixed mu and sigma values for an hidden unit, and these two are trainable parameters. Okay, in this way the batch normalization is applied at the time of testing. Okay,
let us see the code implementation of batch normalization. Now to understand batch normalization, I am using make circles dataset. Okay, I am importing necessary libraries, and this is my entire dataset which contains two classes, one is blue and other is red. And after that I am doing the train test split, and after that I am converting the from numpy to tensors. Okay, I'm converting the data type from numpy to tensors, and then I'm using data loader to apply mini batch gradient descent training technique. Okay, so this is my model without batch gradient descent. Okay, without batch normalization. Okay, initially I'm not applying any batch normalization, and I'm checking out the results. After applying the batch normalization, I'll be checking out the results, and at the end I'll be comparing the both the results. Okay, first I'm using the model with no batch normalization applied, and this is my loss function and this is my optimizer, and you can see that this entire is my training loop and this entire is my testing loop, and these are the model results. Okay, the training accuracy is around 50% and test accuracy is around 50%. Okay, means the model isn't learning much. Okay, now I am applying batch normalization over here. Okay, now after applying the linear layer, okay, after applying the linear layer I am applying the batch normalization as a separate layer over here, and then I am applying the ReLU activation function, because I am applying the batch. Okay, I am doing the batch normalization on the weighted sums, and I am passing it through the activation function. So that is why I have followed this procedure. Okay, first I have used nn.linear layer, and then I have used the batch normalization layer, and then I am using the activation function. Okay, so this is my implementation of the batch normalization. Okay, nn.batchnorm 1d. Okay, this 4 came from this. Okay, now here what integer you have, that integer must be placed over here. Okay, 2 2. Okay, that integer must be placed over here. Okay, in this way I'm applying batch normalization over here. Okay, now this is my loss function and optimizer, and this entire is my training loop, and this is my testing loop, and these are my model results. Okay, the training accuracy is around 73% and test accuracy is around 71%. Okay, initially without batch normalization the training and test accuracy were 50% and 50%, and now after applying the batch normalization the training and testing accuracies has improved to 73% and 71%. Means you can see that there is a huge increase in the training and testing accuracy. Means the model is learning very much excellently. Okay, this is the advantage of batch normalization. Okay, batch normalization in turn will help you gain will in turn help you to improve the performance of the model. Okay,
now finally let us discuss few advantages of using batch normalization. Okay, among them first is stable training. Okay, we have already discussed about this, and second is faster training. Okay, means reduced training time. Okay, we have also discussed about this faster training as well. Okay, our third advantage is show some regularization effect. Okay, now due to regularization effect the overfitting is reduced. Means the model is able to generalize well. Okay, generalize well on the unseen data. Means test accuracy is reduced. Okay, in simpler terms we can say that as test accuracy is increased. Okay, test accuracy is increased. Model generalization increasing means test accuracy is increasing, means it is showing some regularization effect. Okay, we have already seen this in our code implementation where we applied regularization to our model, and we have seen that increase in test accuracy. Okay, means it is showing some regularization effect. And fourth advantage is weight initialization effect is reduced. Okay, now before applying batch normalization, this is our contour plot. Okay, it is in the form of oval shape, and this is our global memo point. Now let's say we have initialized the weight over here. Okay, now when we initialize our weight over here, the gradient descent need to take these many steps. Okay, it takes these many steps, means from here to here the gradient descent needs to travel. Now let's say we have initialized our weight over here. Okay, now when we initialized our weight over here, it need to take, okay, the gradient descent algorithm need to take some fewer steps. Means it is considered from where we initialize our weights. Okay, now when we use, so now when we use our neural network without applying the batch normalization, the weight initialization effect is considered. Okay, the weight initialization effect is shown at the time of training. Okay, now when we initialize a weight here, okay, weight over here, we'll be seeing some different kind of training. Where we initialize weight over here, we'll be seeing some different kind of training. Now when we apply batch normalization, the contour plot is a uniform circle. Okay, uniform concentric circles. Okay, now when the contour plot is uniform concentric circles, no matter where you initialize the weights, the distance to the global minima is same. Okay, it needs to travel the same distance, it need to travel the same distance, it need to travel the same distance, and this also needs to travel the same distance. Means by applying the batch normalization to our artificial neural network, the weight initialization effect is reduced. Okay, here you can see that there is clearly the effect of weight initialization, but here you see that there is no effect of weight initialization. Okay, these are the four basic advantages of batch normalization. Okay, hope you guys like this video. If you like the video, please like, share and subscribe. Thank you.